Now we will consider the basic memory operations. For memory operations, we need the following to have. We need to have data, the data to be written to the memory or to be read from the memory as required by the operation. We need to have the address, which specifies the memory location to operate on. The address lines carry this information into the memory, and usually this address is provided by the CPU. Typically, we have n bits of address lines in order to locate 2 to the power of n words. So with each address, we can determine that the operation is going to be performed on a specific memory element. And obviously, we need to have an operation. What the operation is itself. This is the information to be sent to the memory and interpreted as control information, which specifies the type of the operation to be performed. Typical operations that we have for the memory are the read and write. So we read from the memory and we write into the memory. These are the two main basic operations that we have, and we are going to check them in the next slides. There are also other operations. For example, read followed by write, and a variety of operations associated with delivering blocks of data. Okay, not only a single element, but blocks of data. The read memory operation is an operation which reads a data value stored in the memory. To perform this operation, we need to place a valid address on the address lines. So to determine from which element of the memory we are going to read the data. And then we need to wait for the read data to become stable. So when the data is read and written into by the CPU, written into an internal register, then the operation will be completed. On the other hand, for the write memory operation, it's an operation which writes a data value on the memory. So we need to place a valid address on the address lines and a valid data on the data lines. So these two information should be available, they should be provided, and then the memory write command line should be toggled. And after a while, after a given amount of time, this data will be written into these memory elements with the given address. So data will be written into the memory with the write memory operation. For the read and write operation, sometimes we have the read or write enable line defined as a clock with precise timing information as well. Then we call them as read clock and write stops. Otherwise, they will just be in the form of an interface signal. And sometimes we need to have the memory in order to acknowledge that it has completed the operation. So this is also possible. We have the memory, we ask the memory to perform an operation, and then the memory should acknowledge that the operation is completed. Here we will see the examples of the read and write operation for the memory in terms of the timing. For most basic memories, we have them in the form of an asynchronous memory. So storage happens in latches or in the form of electrical charge in the capacitors, and basically there's no clock inside the memory, so it's not a synchronous circuit but an asynchronous one. Then when we want to have the CPU interconnected to the memory to read the information, to write the information to the memory, the overall thing should be done in a synchronous way. So basically the CPU will provide the address, the data for the write, and the read-write control signal, and also the memory enable. With the memory enable, the whole operation will be kind of synchronized with the rest of the computer system. However, in this example, we will see how this is done. So memory enable is one control input, read write is another control input. For the memory, in order to provide the data, to have the data in the valid form, it takes some time. In the example that we have here, it takes 65 nanoseconds for the memory to provide the information which is required from one of the memory elements. If we consider that we have a CPU with a clock which takes 20 seconds for a clock pass, 20 nanoseconds for each clock pass, then in order to have the read operation completed, we would need to use at least 4 clock passes, as you can see here. Yeah. So these 4 clock passes will be used in order to have the whole read operation performed. 65 nanoseconds of the whole 80 nanoseconds will be used in order to finish the operation, and then there will be 15 nanoseconds spare time. The read memory operation starts with the placing valid address over here. So at the rising edge of the clock T1, on the address line we will have some valid address. This valid address is the address of the memory element from which we want to read the data. Since for the address line we can have ones or zeros depending on where we are just referring, you see that here we have both ones and zeros. So when we have it in this form, it means that for the address lines we may have ones or zeros. But this area which is shaded in blue, the shade in blue means that the data over there is not important for now. But once it is not shaded, it means that the data in this area is important during these 4 clock passes. At the rising edge of the clock for T1, we provide the CPU in it, provides the valid address line, and then the memory is also enabled. So memory enable becomes 1 as well in order to enable the memory. This is also sometimes is referred to as the chip select. We will use this later. Chip select, or CS, is another term which is used for memory enable. Then for the read write control command, it is kept in 1. So 1 here means that we are going to read from the memory. And as I mentioned, after 65 nanoseconds, the information will be valid. So CPU will be able to write this information into some internal register. And then in the next rising edge of T1, we can perform another memory read or memory write operation. But you can see that even after the data, after the time in which the data is provided by the memory, we need to have the read write at 1. So we keep the read write signal at 1, meaning that we are still reading from the memory, and the memory still remains as enable, and the address line has still the same address that we wanted to read from. The same address refers to the same elements from which we wanted to read from. Yeah. Just after this time, then we can change the memory enable goes to false, meaning that the memory is not enabled anymore, and then since it is not enabled, whatever we have in the address line will not be important as well. Similarly, for the memory write operation, we have the timing. So you can see the write timing. It takes 75 nanoseconds for the write operation to complete by the memory. So similarly, 4 clock pulses are used here. In total, until here, in total 80 nanoseconds is used. The operation starts like this. At the rising edge of the clock T1, the address line will be valid. So with this, we determine where we are going to write the new incoming data. The memory is enabled at the same rising edge of the clock. Then after 1 clock pulse at the next rising edge of the clock, read-write goes to down, goes to 0. So when this is 0, it means that writing can be performed. And then it will take a while for the memory in order to write the information, the data into its elements. Then you can see that when the CPU makes read-write 1 again, so meaning that the data will not be written into the memory anymore, the memory enable is still at 1, so meaning that the memory is enabled, and the address line keeps its valid address. This is done in order to avoid writing data into some unwanted element. So here you can see also the critical times measured with respect to the edges of the write pulse. So for the write pulse, we have 1001. This 10 which is mentioned here refers to this time instant 10. So read-write goes from 1 to 0. And you can see that address must be established at least a specified time before 10. So that's what we have here. And then it should be held for at least a specified time after 01. So after 01, you can see that we have it. Let me use another color maybe. So after 01, which is here, this 01 happens over here. We go from 0 to 1. And for a specific amount of time after that time instance, the address must be held. It should be stored, yeah, and it should be kept the same. And this is done in order to avoid disturbing stored content of other addresses, other elements in it. Because if the data in the address line changes, there is a chance that the new elements which are referred to by the new address could lose their data. And then in terms of the data must be held for at least a specified time after 01 in order to write the data correctly. Again, 01 is here. 01 changes here. For the data input, you can see that it should be kept at least for a specified time after this 01. And data valid is also provided here together with the 10 of the read-write control input. So at the same time that we have the read-write going to 0, data should be valid. The data that we want to write into the memory should be valid, and it should remain there for a specified time after 01 for the read-write command control.